Wishes and greetings from Rohini College of Engineering and Technology and myself Manoj. In the last part, we have discussed the problems regarding to the second law of thermodynamics, Carnot engine. Here we are going to discuss another problem regarding Carnot engine. A Carnot heat engine which operates between the temperature level of 927 degrees centigrade and 33 degrees centigrade. It rejects 30 kilojoules of heat to the low temperature sink. The heat pump receives 270 kJ of heat from low temperature reservoir and rejects it to the surrounding at 33 degrees centigrade. Determine the temperature in degree centigrade of the low temperature reservoir of the heat pump. This is one of the complicated problem. We need to understand it very clearly by reading the problem one or more time. A Carnot heat engine. Initially they given us the Carnot engine. How to illustrate the same as a diagram. Here we are having a heat engine. Here we are having a heat engine. The initial temperature, there is a temperature levels of 927 degrees centigrade. We have to convert it into Kelvin as 1200 Kelvin. There is a temperature limits of the heat engine 927 degree and 33 degrees centigrade. How to convert it into Kelvin and place here. T1 is equal to 1200 Kelvin and T2 is equal to 306 Kelvin. It rejects 30 kilojoules of heat to the low temperature sink. Here the heat supplied is not given, but the heat rejected Q2 has given as 30 kilojoule. Therefore, I have represented the Q2 is equal to 30 kilojoule, the heat rejected. The heat pump receives 270 kilojoule of heat from the low temperature reservoir and rejects it to the surroundings at 33 degrees centigrade. That means another device, heat pump, which receives 270 kilojoule of heat from the low temperature reservoir. That means low temperature reservoir means the sink T2. T2 is equal to 306 Kelvin we are having. That from that region, the heat pump receives 270 kilojoules of heat. Determine the temperature in degree centigrade of the low temperature reservoir of the heat pump. So listen carefully. The heat pump receives the heat from the low temperature sink of the heat engine. So therefore, the low temperature sink of the heat engine is equal to the high temperature source of the heat pump. Here it is shown as heat engine, it is simply heat pump. Okay, here it is heat pump HP. You have to remember this. The sink temperature, the lower temperature of the heat engine is equal to the higher temperature of the source of the heat pump. Here they have asked you to find the sink temperature of the heat pump. Therefore, our aim is to find the value of T4. Okay? Yes. Here there is an illustration as drawn as a diagram. Q4, Q3 is a heat extracted or heat rejected in the heat pump. Here the T3 is 306 Kelvin. Since I already told you, this sink temperature is equal to the source temperature of the heat pump. Solution. The temperature of the lowest reservoir T4 we are going to found. And first, efficiency of the heat engine, because since our initial device is a heat engine, therefore we are going to find the efficiency of the heat engine. Efficiency of the heat engine is equal to T1 minus T2 divided by T1. That is the T higher temperature minus T lower temperature divided by T higher temperature. Therefore, 1200 minus 306 divided by 1200. That is equal to 74.5% we get the efficiency of the heat engine. So from this, we have to find the value of the heat supplied to the heat engine, because when you are looking at the diagram, we know the heat rejected as 30 kilojoule, but we doesn't know the heat supplied to the engine. So by using the efficiency formula, work done by heat supplied, we are going to find the value of Q1. Here instead of W, we can put Q supplied minus Q rejected. That is Q1 minus Q2 divided by Q1. Here the efficiency value we found in the previous step, that is 74.5%. When we are substituting the same, we have to remove the percentage by dividing the value into by 100. 0.745 is equal to Q1 is unknown, we doesn't know, minus Q2 is given in the problem as 30 kilojoule divided by Q1. So therefore there is only one unknown called Q1. By solving this, we will get the value of Q1 is equal to 117.65 kilojoule. After finding the heat supplied to the heat engine, here we are going to find the work done, the total work done by the engine. The efficiency of heat engine is equal to work done to the heat supplied. Therefore, the efficiency value we know as 74.5%, that is 0.745 is equal to W, we are going to find, divided by 117.65. So by solving this, you will get the value of W as 87.649 kilojoules. Or another way to find the value of W is equal to Q1 minus Q2. 117.65 minus 30, which is also equal to 87.649. So both the way you can find the value of W, right? Okay, then we are going to find the value of Q3, since the Q4 is given in the problem as 270 kilojoule, because the heat pump receives the 270 kilojoules of energy from the low temperature reservoir. So listen the problem very carefully. They have clearly given the heat pump receives 270 kilojoule of heat from the lower reservoir. That's why from the lower reservoir, from the sink, it is supplied as Q4 is equal to 270 kilojoule to the heat pump. This is not a heat engine. Again, I'm telling this is heat pump HP. Okay, and it rejects this heat to the surrounding of 33, and it rejects the same here 33 degree centigrade, that is considered as 306 Kelvin. So therefore we are going to find the value of Q3. Q4, as you know, 270 kilojoule. The same, the work done formula, that is equal to heat supplied minus heat rejected. Here therefore Q3 minus Q4. Here we know the value of W, we know the value for Q4, the unknown is Q3. So from this you can find the value of Q3 is equal to 357.65 kilojoules, right? The Q3, therefore all the values, all the unknown values we found. Q1 we found, Q2 is given in the problem, Q3 we found here, Q4 it is given in the problem. So there is no unknown values, only T4 is unknown now. Here we are going to find the value of T4. We are going to find as like for the engine we found the efficiency, the same for the heat pump we are going to find the COP value. The COP of heat pump is nothing but the heat rejected divided by the work done, right? Therefore the heat rejected we found in the previous step, Q3 is equal to 357.65 kilojoule to the work done. Work done is also we found in the previous step. W is equal to 87.649, because the work given by the heat engine, the work done by the heat engine is directly sent to the heat pump. Would you understand this? The work output coming from the heat engine, the same goes to the input for the heat pump. This is shown in the diagram clearly. Right? The work output from the heat engine is the same going as a work input to the heat pump. Okay, so therefore we have used the W here, work input. The whatever the work done by the heat engine is directly goes to a work input to the heat pump. Therefore Q3 and W value known. From this you can find the value of COP heat pump as 4.08. Then by using the coefficient of performance formula, that is Q3 divided by Q3 minus Q4, or else T3 by T3 minus T4. That is the higher temperature divided by the higher temperature minus lower temperature. In case of refrigerator, the lower temperature divided by higher temperature minus lower temperature. There should be a difference. We have to keep it in mind. The COP of heat pump is when we are finding the thermal efficiency, the thermal coefficient of performance, the higher temperature divided by the higher temperature minus lower temperature. Here the higher temperature T3 is 306 Kelvin divided by, again the higher temperature is 306 Kelvin minus T4. Here the COP of HP also we found in the previous step. Here the unknown value is T4. By solving all those things, we will get the value of T4 is equal to 231 Kelvin. Here they have given some complication. They are combined. It is a combined heat engine and heat pump problem. So for all the problem, we need to find, in case of heat engine, we need to find the efficiency of the heat engine. In case of heat pump, that is given as COP. We need to find the COP of heat pump. We should not collapse, we should not confuse with the refrigerator and the heat pump. Right? Refrigerator is a device which used to maintain the temperature below the atmosphere. Therefore, its COP is the lower temperature divided by higher temperature minus lower temperature. In case of heat pump, which maintains the temperature above the atmosphere or surrounding, that means the higher temperature, the COP value for a heat pump is the higher temperature divided by the higher temperature minus lower temperature. So another problem, a Carnot engine with efficiency of 0.4 drives a refrigerator with COP ref is equal to 4. Both the engine and refrigerator rejects energy to the atmosphere. Determine the amount of energy rejected into the atmosphere by both the devices for each kilojoule of energy from the cold space by the refrigerator. So compared to the last problem, the one and only difference is in the previous problem it has been given as the heat engine and the heat pump. Here it is given that heat engine and the refrigerator. Here also a small change. Here I have given the heat engine. The second thing is not a heat engine, it's a refrigerator. This is a refrigerator. Here it is a heat engine, right? Okay, now look at the Carnot engine gives the efficiency of 0.4. That is the efficiency of the heat engine is directly given in this problem, and the COP of refrigerator also directly given. Therefore, we have written the given data. Efficiency of heat engine is equal to 0.4 and COP of refrigeration is equal to 4. Both the engine and refrigerator rejects energy to the atmosphere. So both are rejecting energy to the atmosphere. Here Q2, here Q3. Determine the amount of energy rejected into the atmosphere by both the devices. How much amount of energy is rejected by both the devices? This is what the question, right? Okay, listen now. Here we doesn't know any values, the Q1, Q2. In case of heat engine, we doesn't know any temperature or any other thing, but directly they have given the COP and the efficiency value. Here I'm going to find the values of the refrigerator. We are going to find the value of Q2, there is heat rejected from the heat engine, and Q3 is a heat rejected from the refrigerator, right? Therefore, the COP formula is equal to Q4, because as I already told you, in case of heat pump, the higher temperature or higher heat energy comes in the denominator. But here it is a refrigerator. So therefore, the lowest energy comes in the denominator. In case of temperature, it has been considered as T4 divided by T3 minus T4. Right? But here the temperature is not given. Therefore, we have to find the Q, use the Q value. Therefore, Q4 divided by Q3 minus Q4. Here, the COP is known, that is 4 is equal to The Q4 is given as 1 kilojoule. That means 1 kilojoule means here they have asked both the engine and refrigerator rejects the energy to the atmosphere. Determine the amount of energy rejected into the atmosphere by both the devices for each kilogram, each kilojoule. You have to look out this line. Rejected into the atmosphere by both the devices for each kilojoule. Each kilojoule means 1 kilojoule. That is the indirectly this data has given 1 kilojoule of energy from the cold space by the refrigerator. Here this T4 is a cold space. As you know that this is a source and this is sink. This T4 is considered as a cold space by the refrigerator. Okay, here it is a cold space. In this diagram, this is a cold space. Here they have exactly given the heat rejected by both the device for each kg. That means for each kg means for 1 kg of energy from the cold space by the refrigerator. That's why we have taken this Q4 as 1 kilojoule. Would you understand this? Yes. Here we know the value of Q4. Q3 we doesn't know. By substituting this value, COP is equal to 4 is equal to Q4 1 divided by Q3 minus 1. So therefore, only one unknown value called Q3. By substituting all those things, you will get 1.25 kilojoule is a heat rejected by the refrigerator, right? Then we are going to find the value of W. After finding the value of this Q3, we can find the value of W. W of refrigerator. That is the work input to the refrigerator. That is Q3 minus Q4. Q3 value we found in the previous step. 1.25 minus Q4 is 1. Therefore, the answer for W, the work input to the refrigerator is equal to 0.25 kilojoules. Okay. Next, we are going to find the value for the heat engine. Since we found the W value is 0.25 kilojoule, that is nothing but the work input given to the refrigerator. Again, I'm telling this area is nothing a refrigerator. It's not a heat engine. The work input to the refrigerator. That is the work output from the heat engine is same as the work input to the refrigerator. So both the work output from the heat engine is same as the work input to the heat engine, because whatever the work output coming from the heat engine, the same is sent to the input for the refrigerator. Therefore both the W is same, that is shown in the diagram. Therefore the heat engine efficiency formula is equal to work done to the heat supplied. So work done, we have considered this work done, since I already told you the work output from the heat engine is equal to the work input to the refrigerator. Here we found the work input to the refrigerator, W is equal to 0.25. By substituting the same here, we will get the value of heat supplied to the heat engine. Q1 we found. Afterwards, we are going to find the value of Q2. That is W is equal to Q1 minus Q2. The W value is 0.25 kilojoule. It's equal to Q1 value 0.625 kilojoule minus Q2 is unknown. By solving this, you will get the Q value as 0.375 kilojoule. Therefore, the question asked here is the amount of energy rejected. The amount of energy rejected into the atmosphere. That is both the Q2 and Q3. This is the answer we have to find. For finding this, we find all the Q1, Q2, Q3 for all the values. Right? Here we have mentioned Q2 is equal to nothing but the heat rejected from the heat engine, and Q3 is nothing but the heat rejected from the refrigerator. Both the values we found. Thank you.